All right, so let's see if we can finish up this section here in 30 minutes. Actually, less than that, right? So remember that the first derivative test is it's both fine and dandy. The number line chart works great, but it only works for what type of functions? Continuous functions, right? So does that mean that functions that aren't continuous don't have local max or mins? Absolutely not. It still can. The only thing is we can't use the first derivative test to find them or just justify it. So let's take a look at something like this. This is, of course, our favorite type of function, a piecewise function. It's a relatively easy one. It says find the relative extrema of this. What would you suggest doing if we were trying to find the local max or mins of a piecewise function? What have we pretty much done in the past? Graph it. Yeah, let's graph it. So you come over here to x equals 1. It looks like it's the line x plus 3 everywhere except that one. So what would be the limit as x approaches 1? 4, right? We don't have to do the left side of the limit and the right side of the limit separately because it says when x is not 1, it's x plus 3. So that means from the left and right, we can plug into there and we get 4. So I'm going to go to the point 1, 4 and put an open circle. And then I know it's going to pass through the y-intercept of 3, so I'll just put 3 here. We only need 2 points per line, so if I draw the line up to there and then the line up to there, it looks like that. And then at 1, we have a value of 2, which is going to be right there. Okay, so there's the graph. Do we have any absolute extrema? Just review. On the interval of the domain of the function, all real numbers. No, we don't, right? There's no absolute min, absolute max. Do we have any local extrema? Yeah, I think we do, right? If you look at the dot at 1, it's locally low, right? So if you look immediately to the left and immediately to the right, you have values that are taller. So how are we going to justify it? Well, here's what we're going to say. First of all, f has a local min. Do we need to list the y value or just the x value? Well, let's read. Find the extrema. That implies the what? The y values, yeah. So f has a local min. We'll say of y equals. Is it y equals 2 or y equals 4? 2, yeah, it's the actual function value, not the whole value. So it has a local min of y equals 2. We'll go ahead and say at x equals 1. And then because, have we said or shown that x equals 1 is even a critical value yet? No, we haven't. So when we do that up here, when we're actually finding them, saying the derivative is undefined, saying the derivative is 0, and then discovering those values, that's declaring them as critical values. In this case, we haven't declared it as a critical value. The graph doesn't mean anything, right? So we're first going to have to say it's a critical value. Because remember, local extrema can only occur at critical values. So that's part of the justification when you have them already in your possession. Because, what is the function's name? F? Because f has a critical value at x equals 1. And that's another because, we want to say why, because f prime, or how about this? Since f of 1 equals 2, and f prime of 1 equals d and e. So it's almost like we're doing two justifications in one. First of all, we're justifying a critical value. So you could almost do that as a separate argument. First of all, f has a critical value at x equals 1, since it's defined there, and the derivative is not. Okay? I just happen to throw it in the justification for the local min. And since, can we say f prime changes from, since it's a min, can we say f prime changes from negative to positive? No. In fact, that would be a lie, isn't it? Because notice f prime is positive on both sides. So that doesn't work. So all you have to say is, and since f of x is, or how about we'll use math, f of x is greater than 2, which is what we're calling our minimum value. Bless you. on either side. There's that same kind of on either side of x equals 2. So that either has that sense of immediacy. So immediately to the left of x equals 2 and immediately to the right of 2, the function f of x has bigger values. Okay, so you can get by with saying that. And that's the justification, all right? We showed it was a critical value, and then we kind of gave the definition of the local min. Immediately to the left and right, or essentially on either side, the function f of x is greater than 2. Okay, so are there any local maximums, just to be thorough here? No, there's no local maximums. If that value, though, instead of being defined at 2, was defined, let's say, at 12, that value would now be up here, and that same y value would now be, or not the same y value, it's 12 now, but at the same x value, we would now have a local what? It would be a local max, right? And then we would say, because on either side of x equals 1, f of x is less than 2 on either side. Okay, cool. Any questions then on piecewise functions? It's always best if you're trying to answer characteristics of the graph to just sketch the graph. All right, and then it brings us to example 8, where we have discontinuities, but they're not piecewise functions. All right, so be careful of discontinuity. That is where the function is not defined, especially vertical asymptotes. So here we go on example 8. For both functions below, determine, number 1, the intervals of increasing, decreasing, okay, and the x coordinates only of the local max or mins. Justify, okay, sweet. Step 1, find the domain of the function. What's the domain of this function? All real numbers except for 0. So we can say the set of all x such that x ain't 0. It's the easiest way to say it. That's set builder notation. All right, so now it would be helpful to know what type of discontinuity it is. So remember, we can inform ourselves of that in one of two ways. We can factor and see if it divides out. If it divides out, it's removable. It's a removable point hole discontinuity. Or we can just plug into the top and see what we get. Remember, if we plug into the top and we get 0 over 0, it's a hole. And if we get non-0 over 0, it's a vertical asymptote. So what do you get when you plug a 0 into the top? You also get 0. So 0 over 0. So we could say that f has a hole at, and we'll go ahead and list it as an ordered pair, 0, comma, whatever. How do we find the y value of the hole? We need to take the limit, right, as x goes to 0. And so that would be our factor and divide out. So instead of setting it up as a limit, let's just go ahead and simplify this. And there's one on the worksheet that's similar to this. It's the one that Mr. Bird asked me about during lunch. But, of course, it's a little more interesting on the worksheet. If we simply factor the numerator, we get x squared plus 1, and the denominator is x. So you could divide that out, and you can now say that f of x is really equal to x squared plus 1 for all x except 0. So the graph of f of x is going to look exactly like the parabola x squared plus 1, except at 0. Okay? And now that gives us a way to find the y value of the whole, right? So to find the y value of the whole, all we had to do was factor, divide out, and plug a 0 into what's left. So x squared plus 1 is continuous everywhere. So what do you get when you plug a 0 in there? You get a 1. So we don't have to show any notation or anything. We just get a whole at 0, 1. If you had to show the notation, it would be the limit as x goes to 0 of f of x equals 1. Okay, we factor, divide out, and plug in. So let's go ahead and see what that graph looks like, just because we can. X squared plus 1, that has a y-intercept of 1, but we know that that's the open circle now, and it opens up on both sides. So anytime you can get a visual, whether it's in your brain or in your head or in your heart or in your kneecap or whatever it is you visualize graphs, I don't know where that might be, or if you actually draw it on your paper, it informs you as to what the question looks like, or it can help you proceed through the analysis part of it. I forgot what we're doing. We're trying to find intervals of increasing, decreasing. If I can sketch the graph, I kind of know the answer to that question, don't I? So let's go ahead and do it. F is decreasing on what interval? negative infinity to x equals 0, good. And f is increasing on the interval from 0 to infinity. Sweet. Okay. Now it says to find the x coordinates of any locus extrema. Now notice at x equals 0, f prime changes from negative to positive. You see that? Because the function goes from decreasing to increasing. Would it therefore be a local minimum at x equals 0? Not even, right? Because it's not defined there. So do we have any local extrema? There's no local extrema. No local min, no local max. So no local extrema. Do we have any critical values? Or we can have critical values without them being local extrema locations. Do we have a critical value? Is x equals 0 a critical value? The derivative there is undefined, right? For sure, f prime of 0 equals dne. Good, but x equals 0 is not a critical value because it's not in the domain. I would call it a very important value, but in the definitional sense, it's not a critical value. Okay? So there's no way we can have a local min or max there. So I'll just go ahead and say no critical values, even though there's one that we might be tempted to call critical value. Do we have any absolute extrema? For what it's worth. Global max, global mins? Nope. None of that either. So I'll just say no extrema. And of course that means global or absolute. So we answered some calculus questions, right? Increasing, decreasing, local extrema. But did we use any calculus? No, not really. We really didn't use any calculus at all. So is that legal? Heck yeah. So anytime you could generate, again, a graph, you can answer questions maybe more directly, all right? And assuredly as well. Okay, if you were to try and find critical values, you could take the derivative of f of x using the Hodie rule, and you're going to get 0. You're going to get the derivative as undefined at 0. But you'd have to remember that it's not a critical value because it's not in the domain of the function. Very, very important. Okay? Let's see what that would look like. I think we have time. If you were to take the derivative, I probably would not use the Hodie rule. I would probably simplify it. Again, you could do it like this, x cubed over x plus x over x. Oh, that doesn't work, does it? Because then you get it dividing out. Sorry. Let's use the Hodie rule. Yeah, you don't want to oversimplify it. So Hodie, here we got ho. D high is 3x squared plus 1. Ho D high minus high. And then D ho is 1 all over ho ho. So if you simplify that, f prime of x, expanding it, you get 3x cubed plus x minus x cubed minus x all over x squared. This would be someone who's like a robot and they're just jumping in, must take derivative, right? They haven't really thought about it beforehand. 2x cubed, and your x's cancel, so you're left with x squared. Now, if you leave it like that without simplifying, you might say, okay, f prime equals dne when the denominator x squared equals 0. Well, that's when x equals 0. So we have a critical value at x equals 0. And then you're going to be like, I know that it can also equal 0, so f prime equals 0 when the numerator 2x cubed equals 0. Well, that's when x equals 0. So as I mentioned, x equals 0 is a critical value. Look at that. We've confirmed it twice. X equals 0 is a double critical value. That's like a super critical value. But is it at all? No, it's not. So notice how he's going to try and sneak in. He's going to try and sneak in, but it's not going to work. He's not a critical value because he's not in the domain. If you simplified that, of course, you get 2x. Now, let's say we wanted to do a number line chart just because we wanted to know where the function's increasing, decreasing. Okay? Let's say we don't know what the graph looks like. We can still make a number line chart. We got x and f prime. And even though we don't have any critical values, what other numbers always go into a number line chart? Discontinuities always go into a number line chart. We haven't had any yet, so this will be the first time. So that's x equals 0. Now, here is a helpful hint. When you put a discontinuity in the number line chart, don't put it in like that. Whether it's a whole or a vertical asymptote, I recommend putting it in as if it were a vertical asymptote, like that. Why? If it's not in the domain of the function, that's going to be a visual there to remind you that it's not going to be a local maximum in. Okay, so there's a -1, there's a 1. I'll plug it into my derivative f prime, the simplified version, which is 2x. You plug in a -1, you get negative. You plug in a +1, you get positive. So there you go. You can get the intervals of increasing, decreasing, flying blind like that without knowing what the graph looks like. But here's then where you again have to be totally aware about what's going on at 0. When you don't have the graph to look at, it's easy to kind of forget that x equals 0, being in the number line chart, is not a critical value. And then you might say, oh, it goes from decreasing on the left to increasing on the right. It must be a local minimum location. And, of course, it's not. All right? So there you go. I think I've made my point about discontinuities. Find them first. Be aware of them all the way through. They do go in number line charts. We don't have any other critical values here to put in there with it, but you can put it in there by itself to figure out intervals of increasing, decreasing. Okay. Last one. We got time. We got f of x equals that. So the way it sits, let's find the domain. Okay, domain. No logs, no square roots, no fourth roots, but we have a denominator with an x squared in it. So once again, x cannot equal 0. Let's determine what type of discontinuity it is. If you plug a 0 into the top, you get what? 1, or -1 if you distribute that negative through there. So you get -1 over 0. Non-zero over 0 means what? Vertical asymptote. So there's a vertical asymptote at x equals 0, or f has a vertical asymptote at x equals 0. All right, so right away, is 0 then going to be a critical value? No. Is it going to go in the number line chart, though? Yes. Okay, good. We got that. We're aware of that from the beginning. Now, do we know what that graph looks like? Well, I'm not quite sure I know what that graph looks like. If you want to try, you can split it up, x to the 4th over x squared plus 1 over x squared. That's going to give you a negative parentheses x squared plus 1 over x squared. Anyone know what that graph looks like? A parabola plus a volcano graph combined? No idea. I have no idea. So it's not going to be something that's going to help me like it did over here. So I'm just going to kind of get rid of that. I'm going to go ahead and find my critical values then, if I have any, just by using calculus. So how do you want to handle that negative? You want to leave it up front, or you just want to distribute it through the top, or put it in the bottom? Leave it? Yeah, okay. So let's use the Hodie high rule. F prime of x is negative beefy brackets. Okay, that's what I would do. And then Hodie high of the rest of it. So you got ho is x squared, d high is 4x cubed, Hodie high minus high is minus the quantity x to the 4th plus 1, d ho is 2x, all over ho ho, that's x to the 4th. All right, so that negative is still out front. Let's simplify. Keeping that negative out front, I get 4x to the 5th minus 2x to the 5th minus 2x all over x to the 4th. And then I combine like terms. 4 minus 2 is 2. That's impressive. So I get 2x to the 5th minus 2x all over x to the 4th. And we could factor out an x, right? We already know that x can't be 0. It's a vertical asymptote. So you might as well factor it out and make life easy on yourself. So let's factor out a 2x, actually. And that makes it x to the 4th minus 1 all over x. Those divide out. So again, we're investing a lot of time and energy into the derivative, just like home builders do with the foundation of a house. So now that I have a 2 up there, I think I'm just going to put it, well, we don't have a denominator anymore, actually, do we? So it's just negative 2 times x to the 4th minus 1. Did you do that right? Oh, it's x cubed. Yeah, I thought I lost them. I lost too much. Yeah, it's x. Yeah. Okay, good. Well done. Well done. So it's that over x cubed. Sweet. Okay, thank you. Very good. Nice. Now, it's not completely factored, because if you notice, the numerator is still a difference of squares. But if I factor it into x squared minus 1, x squared plus 1, then x squared minus 1 could be factored some more into x minus 1, x plus 1. It's simple enough as x to the 4th minus 1 that I think I'm just going to leave it like that. Okay, so going down this fork here, we consider where f prime equals d and e. Well, that's going to be when x cubed equals 0. That's when x equals 0. He's trying to sneak in again, guys. You see it? Is he a critical value? No. Okay, so I'm going to cross him out. We've already got 0 on the roster. He's going to be in the chart as a vertical asymptote. Your discontinuities that are not in the domain, they are going to try and sneak into the critical value club. All right, because the derivative is certainly undefined when it's undefined itself. So now we'll say f prime of x equals 0 when negative 2 times x to the 4th minus 1 equals 0. And now, since I'm breaking that down, I can divide both sides by negative 2, and I get x to the 4th equals 1, which is when x equals what? If I take the 4th root of 1, do I need to consider plus or minus? I do. Anytime you take the eventh root of a number, you need to consider plus or minus. Okay, because negative 1 to the 4th is 1 and positive 1 to the 4th is 1. So, are those critical values, both of those guys? Those are critical values. Yeah, because they're in the domain and they cause the derivative to be 0. All right, so now I'm ready for my number line chart. I'm going to come up here next to the derivative. I'm going to use this version here. And I got x and f prime. And here I go. I've got negative 1 and I've got positive 1. Is that my number line chart, or am I missing something? You're missing 0. Good. So I'm going to put it as a dotted line. There we go. That's a reminder that it can't be a local extrema. But it can affect the sign of f prime, so I need it in there. All right, how about negative 2, negative 1/2, positive 1/2, and 2? All right, so now I'm going to plug it into f prime. So if I go negative 2 to the 4th, that's going to be 16. 16 minus 1 is 15. 15 times negative 2 is negative. And at the bottom, negative 2 cubed is negative. So I get a positive there. If I plug in a negative 1/2, negative 1/2 to the 4th is positive 1/16. 1/16 minus 1 is negative. So that negative times the negative 2 makes it actually a positive in the top. And the cube root of a negative is negative, so that becomes negative. You don't want to go too quickly through this. If you plug in a 1/2, you're going to get in the top a negative times a negative again, which is positive. And then in the bottom, the cube root of a positive is positive, so you do end up with a positive. And then if you plug in a positive 2, you're going to get a negative over a positive, which is a negative. Okay, real quickly, I'm not going to write out the justifications because we're going to run out of time. But negative 1 is a critical value, yes? And it's a horizontal tangent, so that's going to be the location of a local maximum since f prime changes from positive to negative at x equals negative 1. You can also clump that in the same argument with 1. So you could say f has local maximums at x equals negative 1 and positive 1 since f prime changes from positive to negative at x equals negative 1 and positive 1. Does f have a local minimum at 0? No. Now, if you put 0 in there and you put it as a solid line, you might forget that it was a discontinuity. And then if you go ahead and claim that there's a local min at 0, you're going to get it wrong. Okay? It's a vertical asymptote, and what the graph is doing is it's decreasing on one side and increasing on the other, but it's not a local min. Now, there was an AP question like this several years ago, and if you did not consider the vertical asymptote, notice what's going to happen. If you pick a number between -1 and 1, you might choose 0, but it's not going to work. So if you only choose the -1/2, you're not going to see this plus sign right here that I'm scratching out. And you're only going to get one local max because you're not going to see a sign change here. Similarly, if you then chose maybe +1/2, that you're not going to see that negative sign, you're only going to get the local max on the right and not the local max on the min. So that was like a double penalty in that year. You lost a point for not considering 0, and then you lost another point for missing one of the local max or local mins. So very, very important. If you have a discontinuity, it needs to go in the number line chart. It won't be if it's not in the domain a local max or min, but it affects the sign of f prime. So very, very important. Okay, we got it all in there. That is the end of this section. We might have a tiny little quiz tomorrow. Enjoy the rest of your American Smokeout Day.